right, this is AQA AS Level Physics 2023 Paper 1. As per usual, I can't show the paper on screen, otherwise AQA will copy strike my channel into the grave. So link to the paper and mark scheme are in the description for you to follow along. We have a table of various particles. Okay, so we have a kaon, that's K minus, interacting with a proton, making an omega minus, whatever that is, I can't remember off the top of my head, plus a K0 plus a mystery particle Y. All right, complete table 1. All right, okay. So I'm just going to put it here then. So I'm going to say baryon number here. Now a kaon is a meson. That's something you need to remember. It's a meson that has a strange quark in it. It has strangeness. So if it's a meson, then it cannot be a baryon, because baryons have 3 quarks, whereas kaons, mesons have 2 quarks. So it's got to be 0. We have plus 1 there for the proton, as it says, plus 1 for the omega. That's a baryon, it seems, as well. And well, a kaon again is going to be 0, isn't it? So if that's the case, then that means, they've already got the 0 for us there, which is kind of nice. I should probably do these in black because they're already there. And yeah, so that has to be 0 as well. Next we have charge. What is the charge? So it's -1 for the K minus. Obviously I'm going to drop the E because we don't need it, it's all relative in it. And +1 for the proton, of course, and -1 for this omega minus, whatever that is. When it's a baryon, probably a baryon with strangeness, I'd guess. And kaon is 0, of course. That's what it says already. And so therefore, this mystery particle Y, well, how much charge do we have before? We have 0 before, and we have -1 here. So therefore, in order for charge to be conserved, this must be +1. Then we have strangeness, -1, 0 goes to -3. Oh, okay, so that's strange. Plus 1 there. And so therefore, well, does strangeness need to be conserved? Oh, yes, because it says it's a strong interaction. And that's something you need to remember. If it's a strong interaction, that means strangeness is conserved. It's only in weak interactions that strangeness isn't conserved. And so therefore, well, let's have a look at strangeness here. So we have -1 on the left, -1 plus 1. So we have -2 on the right there already. So therefore, whatever Y is must be +1. So it must have an anti-strange in there. Okay, 1.2, calculate the rest energy of the omega minus particle in joules. Okay, right. So we have the rest energy is, what's that, 1,672 mega electron volts. And so therefore, well, we know we want a small number because joules are big, so we want fewer of them. You can go around the houses by, converting to electron volts and then go from there. But you should remember that the conversion factor for mega electron volts is 1.6 times 10 to the -13. I mean, it's just a power of 6 different from just electron volts, but it saves you a few seconds. It's worth remembering that one. And so therefore, if we want a smaller number, then we're going to be multiplying, aren't we, by 1.6 times 10 to the -13. And that gives us well, seeing that they've gone to 4 sig figs, we probably should too. So 2.675 times 10 to the -10 joules. Question 1.3, suggest how energy is conserved. Oh, great. So we have to look at the thingy. So therefore we have before, just going to be adding these up. So that gives us a total energy before of 1,432.1 mega electron volts, and then afterwards, okay, and that gives us 2,663.6 mega electron volts. So therefore we can say that rest energy of products is greater than the rest energy of the reactants. I don't like using the term reactants, but there we go. They'll accept that. So the question is, where did this extra rest energy come from? Well, we know that essentially, whenever we have a nuclear reaction, there's rest energy and there's kinetic energy involved as well. They are interchangeable. The difference will have come from the kinetic energy of the products of the reactants. Therefore, we can say the EK of the products is less than the kinetic energy of the reactants. There we go. Silly question, seeing that we're not being asked to calculate anything, but whatever. Okay, the quark structure of the omega minus is SSS. I told you. That's because its strangeness is -3. Strange quarks are strange. They have a strangeness of -1. Okay, so it's unstable. It decays into a proton via 3 processes. I think that's a phi, isn't it? Deduce the quark structure of the lambda 0 particle. Ooh, this is pretty tricky. I mean, it's a 4 marker, so okay. Let's go for the first one then. So we have omega minus going to the phi 0. Is it a phi? Oh no, it's not a phi, it's a xi. That's right, weird. It's one that we very rarely come across, just in general from the Greek alphabet. Okay, so we have SSS, and then that's going to a pi minus. Now a pi minus, a pion, is a meson without strangeness, so it's just made up of up or down quarks, or their anti-quark variants. If this is a pi minus, then this has to be a down anti-up, because we have to have a minus 1/3 from the down, and then another minus 2/3 charge from the anti-up. So there we go. Oh, okay. So that means that this one here, so the important thing that you need to remember about this one here, they love testing you on this these days. So total strangeness can only change by 1 in a reaction, interaction, whatever. And so that means that because this has a strangeness of -3, this must have a strangeness of -2. And so therefore we can deduce that it has to have 2 strange quarks in it. However, that would mean that its overall charge would be just, so that's -1/3, that would just be -2/3. But it needs to go up to 0 because it's 0 up here. So therefore we must have an up quark in there as well. Okay, so we've got that. And then let's go for the second one. And so that Zion, oh, that's cool. Zion, reminds you of the Matrix. Zion. Plus pi 0. Okay, so therefore we've got this SSU going to, again, we have the whole strangeness can only change by 1. So that means that this is -2. This has to have a strangeness of -1. So it can only have a strangeness, it only has 1 strange particle in there, strange quark rather. And the pi 0, that could be up anti-up or down anti-down, I guess. I don't think it matters, does it? Don't think so. That's okay. And so therefore, if we know that we've already got a charge of -1/3, go for orange here, so -1/3 for the strange quark, and we need to get to 0, that must mean that we also have a down quark in there to get it down to -2/3 altogether. And then, of course, similar to above, we just add in the up quark there. So UDS is the makeup of the lambda 0 particle. That's it. That's how we write it. It doesn't really matter what order you write them in, but that's generally how we write it by convention. Not a super easy one, that one. Got to remember your strangeness rules. They love testing you on them these days. 1.5, we have the products of the decay, include pi 0 and pi minus. Fine. The pi 0 just turns into gamma photons. And so that's kind of crazy, isn't it? So they can do that? They can just decay without annihilating? Or is it because the up and anti-up or down anti-down inside, they annihilate each other? That's something that I've never come across before. Kind of makes sense, I guess. But usually we talk about annihilation being, 2 particles. But I guess there's 2 particles inside of a pi 0. Whatever. What are we being asked? Each of the photons have a wavelength of 1.25 times 10 to the minus 14 meters. Calculate the energy of one of these photons. Easy. We know that E is equal to HF. And so, well, if we're dealing with wavelength instead. We know that c equals f lambda or v equals f lambda, but if we're talking about the speed of light, which we are in this case, then we might as well go with c equals f lambda. So f is equal to c divided by lambda. So therefore E is equal to h times c over lambda. So that is 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 divided by this wavelength. Ooh, that wasn't a good line. Can I sort out powers of 10? Why not? I'm going to take minus 14 off the top and add that on to here. So that's just going to give us minus 20 on top, and then 8. Let's just add on 8 onto that as well. I'll tell you what, let's just write it over there. So it's going to be minus 12. Of course, you don't have to tidy up powers of 10. It just saves, I don't know, a little bit of time. It is a useful thing to get into because some questions do require that. So I get 1.59 times 10 to the minus 11 joules. 1.6, what could be created when the pi minus decays? Okay, so pi minus, let's go for the first one. So we have a muon plus a muon neutrino. I don't think that's going to look very good, is it? Why is that? Well, it's because of lepton number. Lepton number of a muon is a heavy electron. The electron is the OG lepton, blah, 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 blah. So that has +1, and then this has +1 as well. So no bueno. Let's go for number 2. Is this promising? Yes, I guess it is looking a little bit more promising. So we have an electron and an anti-electron neutrino. Of course, the lepton number of a pion is 0 because it's not a lepton. So we have -1. So we have lepton number +1 and then -1 here. So that checks out because, of course, it's 0 there. What about charge? What is the charge? I've got to stop saying that. That goes to -1 plus 0. So I think that one looks all good. Shall we check the others real quick anyway? So we have, oh yeah, definitely not this one. For the same reason that the top one isn't allowed, is because the lepton number is +1 and +1. No good. And then finally we have it's just going to a bunch of electrons and positrons. And that's not going to work out, is it? Because of the same reason, because of lepton number. So lepton number is +1, -1, +1. That doesn't add up to 0, which we must have. Oh boy, we've got some refraction now. They really are making the refraction questions mean these days. Ugh, this one looks pretty mean too. Bloomin' heck. So we've got that, and that, and that, and light is going in. Boom, boom, but then it's doing this malarkey. Oh my days. And then I guess it's going to come out, whoops, parallel to this one here, isn't it? Okay, what are we being asked? Oh, we've got A and B. When the light is incident normally, okay, so in other words, basically we're being told that when the light just comes in the same direction as the normal, they come out the same way and they interfere. Okay, so I think we get, actually this isn't a refraction question at all. I think this is interference, to be honest. Assume that the light is normal. Okay, so we don't really care about this then? Right, the figure shows this graph. And we have this A and we have B. So they are in antiphase there. Pi radians out of phase with each other. The light has a wavelength of 356 nanometers, and the thickness of the layer is 89 mil. So that's that there. Oh, I misread that. Silly me. It's 89 nanometers. That makes a little bit more sense now, doesn't it? There we go. Okay, so we're talking about a path difference. So how much further has B traveled than A? So I don't think we even need to reference the graph at all, because you know, that shows us that they're out of phase, so whatever. So path difference is equal to 2 times the thickness, because it's going down and up to meet rate A. So that's 2 times 89 nanometers, and so that's 178 nanometers. Oh, this looks pretty good. And so that is equal to half a wavelength. Can you see that? 178 times 2 gives us 356. So basically, B has traveled an extra half a wavelength. So that means that therefore waves meet in antiphase at the surface, therefore destructive interference. Okay, we now have a bit more of a funky graph. They're not quite in... Oh, I can do better than that. I can actually get us to do lines. Clever me. That wasn't very good. There we go. So that one goes there. And then this one is, oh gosh, this kind of a weird phase that it's got going on. This isn't going to be very accurate drawing, just to show you what's going on. Okay, so that's A, and that is B. Calculate the resultant of the waves. What? That's a really stupid way of putting it. Calculate the resultant of the waves. What it should say is calculate the resultant amplitude of the waves at time P. Okay, so at time P, which is like right there, A is at, what's that? It looks like it's 0.9, I think. And then B is at minus something. 1, 2, 3, 3.5. And so therefore, the difference in amplitude is 0.9. Oh, I forgot to put minus in there. That is important because the resultant is always adding, but we're adding minus 0.35. And so that gives us 0.55. I don't know where they, don't know how they think you can measure to 1/10 of a square according to the mark scheme. If you're a normal person, you'll get my answer. 2.3, we're being asked to calculate what the time interval is. We've been given the phase difference as 137 degrees, and we're being asked to find out the delta t, as it were. And we've been given the frequency as well as 4.72 times 10 to the 14 hertz. Okay, now it's quite unusual for us to actually be given the phase difference and then actually have to work backwards. Quite often we have to calculate the phase difference. But let's write down what phase difference actually is. How is it calculated? Now, this isn't an equation that's in your formula sheet. It's just something that it's worth remembering. Phase difference is just a ratio. It's just the bit divided by the lot. It's just a ratio. It's just a proportion. So it's either the difference in time divided by the whole time, that is the time periods of the waves, or it's, if we're dealing with distance and wavelength instead, it's difference in distance divided by the wavelength. And then we multiply either of these by 360 to turn it into degrees, or by 2 pi to turn it into radians. In this case, we're dealing with time period and stuff like that, and we're dealing with degrees. So there we go. So let's write out this again. So phase difference in degrees is equal to delta t divided by big T times by 360. However, we haven't been given the time period. We could calculate it because we know time period is equal to 1 over frequency. They're reciprocals of each other, but let's just substitute it straight in, shall we? So phase difference is equal to delta t times by f times by 360. But we're looking for delta t, so therefore delta t is equal to the phase difference divided by the frequency times by 360. We've been given the phase difference, and then we just divide that by the frequency and also by 360 degrees. And that gives me 8.06 times 10 to the minus 16 seconds. 2.4, okay, we actually do have refraction now. Calculate the refractive index of the material of the layer. Let's have a look real quick. So, well, it's going to be to do with speed, isn't it? So we know that refractive index is equal to speed in air, or let's just put c, divided by c in the medium. Speed of the light in the medium, you might see it as c over cs in your formula sheet. Okay, so the question is, where are we going to get this speed from? Okay, so we're going to have to do the whole, okay, so we're going to have to use the thickness again. Right, so this speed is going to be equal to f lambda. So then how do we find lambda? Oh, no, we don't even have to do that, do we? We don't even have to do that. I'm getting myself all confused. We have the time it takes, time taken to travel down and up. Cool. So therefore, we can literally just use this. Not very often we use this. So just speed equals distance over time. That's all we're talking about. So in this case, it's c, speed of the light in the medium, is equal to 2 times the thickness. I'm just going to put 2 times the distance. I don't want to get confused. Divided by this time interval And so there's going to be 2 times the 89 nanometers, so 89 times 10 to the minus 9, 89 times 10 to the minus 9, divided by time period of, not time period, our time interval of, let's go with that, let's go with 8.1 times 10 to the minus 16. I'm going to put this on top, so that's going to end up being 7 on top. This looks promising. Looks like we're going to get a pretty good number, methinks. So that gives me let's go with 2.2 times 10 to the 8 meters per second. It's slower than 3 times 10 to the 8, and it looks like it's going to give us a good number. So using our equation for refractive index, therefore n is equal to 3 times 10 to the 8 divided by 2.2 times 10 to the 8. And of course we can just forget those, and we're going to end up with a number greater than 1, but it's not going to be too much greater than 1, which is what we want. So something like 1.36. Cool. Question 3. Oh, that's lots of writing. I'm not reading all that. Guess I'm going to have to. We have a lake. Oh, it's very serene. Why can't we just stay there? Why do we have to answer a question about this? It's difficult to see submerged objects. You need to polarize the sun. Oh, we are actually talking about polarizing. Okay, because I do photography, and if you want to see below water, you have a polarizing filter on the lens, and it blocks out the reflected rays that are coming off the water because they are polarized, like the question's saying. Puts on Polaroid glasses. There we go. The amount of light is significantly reduced. Makes sense. Explain what the student can now say. Okay, cool. Oh, well, there we go. I've just answered it, but let's actually write it down. Waves reflecting off surface are horizontally polarized. You don't really need to say that they're horizontally polarized, but it is sort of like skimming a stone. If you spin it sideways, it will bounce off the water. Horizontally polarized, therefore only oscillating in horizontal plane. So the light from the sun is oscillating like this, and all sorts of directions. But when it comes off the water, these ones stop, and then these ones carry on going. They get reflected. Waves reflecting off submerged objects are unpolarized, oscillating in all planes. Glasses have polarizing filter that block waves oscillating. I could say in all planes, or I could say orientation. So same thing here, filter that block waves of certain orientations, in this case horizontally polarized waves, whereas waves oscillating vertically from objects pass through. So there we go, that'll probably get us our marks. Now, it is worth me mentioning, because this is causing a lot of confusion, especially on like the Waves video. You don't need to know which way around the lines are in the Polaroid glasses, but I can tell you that in order to stop horizontally polarized waves, the lines will be horizontal in the glasses. I used to get this wrong as well. I used to think, oh, okay, so doesn't that mean that if the slits are horizontal, that means that horizontally polarized waves will go through? No, because they're not physical objects, are they? They're waves. In essence, what happens is that black lines in filter, as it were, contain electrons that absorb the waves, because that's how these waves are blocked. They have to be absorbed by electrons that absorb waves. In essence, what we can say is those able to oscillate horizontally will absorb waves. Does that make sense? So if the wave comes in like this, that means that the electrons inside can wiggle side to side. It's a very Mickey Mouse way of explaining it. You never need to talk about this in an exam. Polarization is one of the weirdest things in physics. But that's a good way of thinking about it, okay? It's the electrons in the lines, they need to be able to move in order to absorb these horizontal waves. So that means that the vertical waves, of course, will just pass straight through to your eyes from the objects, etc. If you still don't believe me when it comes to the whole, horizontal and vertical polarization and all that jazz, just think about it. If you have something like a microwave transmitter and you have an antenna, and it's vertical, which way are waves polarized coming from it? Of course, they're vertical, aren't they? And so if you want to receive those signals, are you going to have a receiving antenna that's horizontal or vertical? It has to be vertical, of course. And so there we go. A vertical antenna will produce vertically polarized waves, and it has to be the same when absorbing them. Basically, it's not like a piece of string going through slats in a fence, as people quite often talk about waves being polarized. Anyway, you get the idea. Moving on. Okay, bit of resolving forces. We have a bow, we have tension there, we have tension there, and we have our angles, and then we have this force going there. Okay, it's good that it's symmetrical. That saves us a lot of hassle. The force is 160 newtons. What are we being asked? We're just being asked to calculate the tension. Easy peasy. So what we can do in essence is just split this up into 80 newtons and 80 newtons, because that 160 newtons is responsible for producing 2 lots of the tension. That means that in order for 80 newtons to be going that way and that way as well, then that means that it's balancing 80 newtons being pulled this way and 80 newtons being pulled this way by the 2 lots of tension. And then we can just split the whole thing in half. Let's redraw it real quick. So we have our 80 newtons component of the tension going that way. And then we have our tension, which has to be there. Of course, the tension is going to be greater, isn't it? And there's our angle of 75 degrees there. So nice and easy. Tension is equal to 80. And then we're going to use our simple easy vectors resolving trick. If you don't know it, have a look at my video. It's way, way better than drawing triangles. Trust me, you don't even know. So are we going to be using cos or sine? Well, we're turning through the angle, as it were, to get from one to the other. So we're going to be using cos. But are we going to be timesing or dividing? Well, we know that cos and sine are just a ratio between 0 and 1. We know we want a bigger number than 80, so therefore we're going to be dividing by cos 75. And that gives us, oh, that's quite a big difference actually, so 309 newtons. Mark scheme goes 226 figs as per usual, so it says 310. You get the mark for 309. Okay, we have a graph of force against S. The heck is S? Oh, it's the distance that is pulled back. RTFQ site shorts flipping heck. Okay, so let's just sketch this. Oh, that's not a good line. Ow. Everything you do is an epic fail. Whatever, I'll do. Okay, so we have force there, we have distance there. All right, so the mass of the arrow is 21 grams. I'm just going to write that as 0.021 so I don't have to convert it later. The archer pulls back a distance of 0.22 meters. So let's find out what that force is right now. So 0.22. Oh, he's getting a maximum force. Well done there, lads. And that gives us 200 and... what's that? Each one's going to be 4. What a stupid scale. That is a really stupid scale. If you were in my class and you made this scale, I would dog you some marks. So 204, 208. That's so stupid. That's such a bad scale. And what are we being asked? Determine the initial horizontal acceleration of the arrow. Oh, okay, cool. So F equals ma. Oh, it's so easy. So therefore A is equal to F over m. So 208 divided by 0.021. I think it's going to be a pretty fast acceleration. Woo! It is booking it. Wowzers. So 9,904 meters per second squared. Of course, if you want to round it, we can just call it that, can't we? Easy peasy. 4.3, we have a different mass. Oh, we have the energy stored. Oh, okay. The energy stored is 64 joules. And F is 160 newtons. I think this is a work done question. Energy and forces always is. So let's go back to the graph. 160 newtons. Okay, well, that's easy to read off, thank goodness. S is 0.1 meters. What are we being asked to find? Oh, it's just the distance. What? Oh, we can't do that. We can't use work done. Ugh, silly me. Can't use work done because force isn't constant. We can't use the equation anyway because as we pull it back, the force is increasing. But we can use the idea of work done. That is E equals FD, or F equals FS in this case. And so therefore, if we have a graph of these two, that means that energy is going to be the area under the graph equals work done, and therefore energy stored as well. Yay, we're going to have to count some squares. Oh, actually, it's just a nice triangle. Is it a nice triangle? Yeah, I'm going to say it's a nice triangle. I don't care. And so we're talking about this, aren't we? There. So that is 0.1 and 160. Oh, so it's just going to be half that then, isn't it? Cool. So therefore energy. Oh, wait. Okay. Just took me a minute to figure out this question. Look, we've been told what the force is. It's 160 newtons, and so it's just like, oh, I just immediately, like a lot of people, just went, oh, it's got to be 0.1. However, look, if we actually do that, if we actually get the area under the graph for 0.1 there, it's just a triangle. So for 0.1, it's going to be energy is equal to a half times the 160 times 0.1. So that's just going to be 80 times 0.1. So that is 8 joules. That doesn't make sense. It has to be 64 joules, doesn't it? But look, the 160 newtons also crosses the line over here as well. That's the point. And so if we go across to there, we find that the line crosses at 0.385. So that has to be, so S must be instead where it crosses again, so that's 0.385 meters. The problem is then is that you probably do have to count squares in order to actually prove this to be the case. Let's have a look. So 1 square is equal to, that's just going to be 0.05. Let's go with force first. It's going to be 20 newtons times by 0.05. So that actually does give us 1 joule. Each block on this graph is worth 1 joule. And if you actually get the graph and you start counting the squares, so 1, 2, 3, 4, 5, what you find is that there are approximately, if we go to that 0.385 meters, it's approximately 64 squares. And so that does actually check out. That's a dumb question. I don't like it. 4.4, the bow has an efficiency of 0.82, 82%. The arrow leaves the bow in a horizontal direction with a velocity of that. Okay, so V is 190 kilometers per hour, and so that is 1.9 times 10 to the 5 meters per hour. And so then divide that by 3,600, we'll get that in meters per second, which is what we want. Divide that by 3,600 and that will give us it in meters per second, which is what we want. So 52.8 meters per second. Sanity checking that. That sounds like a reasonable velocity for an arrow. We're just being asked to calculate M, and so of course it's going to be energy then, isn't it? So kinetic energy is equal to half mv squared. We're looking for that. But the thing is that we need to take into account our efficiency dealio. It's a little bit tricky to wrap your head around this one. So we know that energy stored equals kinetic energy. However, we know that not all of that energy stored is going into the kinetic energy. So in our case, it's going to be 0.82 times by the energy stored gives us the kinetic energy. So 0.82 times the energy that we got from before is equal to half mv squared. And so therefore, rearranging this, we find m is equal to 0.82 E divided by, oh, I missed the 2 off there. There we go, divided by v squared. So that's going to be 2 times 0.82 times by 64 divided by that 52.8 squared. Not an easy question, this one, but when it comes to efficiency, it's always worth writing it down in terms of this. You go, this energy equals this energy, or that would be the case if it wasn't for the fact that we times by the efficiency. And what do we end up with? We end up with a mass of 0.038 kilograms. Oh yeah, we got fluids and momentum. I love this stuff. Okay, we have a velocity, a gas velocity of 17.2 meters per second. We have the surface area of 1.2 meters. That's the diameter. So therefore, we're going to say pi d squared over 4. That's pi r squared, but putting d in there instead. Is it worth us doing that? Yeah, let's do that. Why not? So I'm going to say pi times 1.2 squared divided by 4, and that gives us a surface area of 1.13 meters squared. Okay, what else have we been given? Oh, we've been given the density, of course, and that's 0.02 kilograms per meter cubed. We're just being asked to show that it moves approximately this. Okay, so we're being asked for actually not the momentum this time, for the momentum carried per second. We're not being asked for the force. We're just being asked for delta m over t equals question mark. That's what we're being asked to find out here. With this kind of question, units are your friends. So we're looking for kilograms per second, aren't we? So we have kilograms per second, we have kilograms per meter cubed, and we have meters squared, and we have meters per second. So, you know, you can go around the houses if you want to, but I would just use your units in this case. So therefore, we're looking for kilograms per second. So we're going to start off with this 0.02 kilograms per meters. We must have that in order to have that kilograms in there. But then we need to get up to, well, we need to get rid of the meters for starters, don't we? So we're going to multiply by 1.13 meters squared. So that gets rid of 2 of those. And then we need to get rid of the meters to the -1 and add in there seconds to the -1. So we're just going to multiply by 17.2 meters per second. So that gets rid of the meters, and we end up with kilograms per second. There we go. There is a sort of another way that we can think about this, several ways that we can think about this. You might remember, this isn't in your equation sheet, but the force is equal to rho AV squared. So in this case, we've just done rho AV. And that is because force is equal to rate of change of momentum. And so that's mv over t, or in other words, that's m over t times by v. And so actually you can see that that m over t, if we're just talking about that, is p rho av rather, without the squared on top. If you don't understand that, have a look at my momentum video, my mechanics video. It goes through that much better than I'm doing it here. So 0.389 kilograms per second. Calculate the mass of the helicopter. Okay, so now we are actually going to have to employ our whole thing. So like I said, force is equal to rate of change of momentum, or just ma, that's fine. And so we can say that's mv over t. And so in our case, we have a constant v, but it's the mass that's changing, as it were. And so we have that. So this is equal to rho av, which is what we just calculated up there, times by another v. And so all we have to do is take our number that we calculated up there and then multiply by the speed again. Easy peasy. And that gives us a force of 6.69 newtons. Okay, we're not quite done because we've been asked to calculate the mass of the whatever. And oh yeah, we're told the gravitational field strength on Mars, we do need that, is 3.72 newtons per kilogram. Cool. So we have the drone there, whatever, and we have the weight pulling down. Why am I writing W? I should be writing mg. And so therefore we must be having a force that is equal to mg pulling upwards. So therefore F is equal to mg. If it's hovering, it is hovering, yeah? Yeah, hover. And so therefore M is equal to the force produced by the props divided by this very low gravitational field strength. And I think we're going to do it with something like 1 point something, and that is equal to 1 point, let's call that 1.8 kilograms. There we go. 5.3 battery stores. Ooh, we got some electricity finally. So the energy is 0.035 kilowatt hours, lasts for 39 seconds. The battery has a power output of 340 watts. Determine the percentage of the initial energy stored in the battery that is transferred during the flight. Oh my days. Of course, we need to change the kilowatt hours into essentially watt seconds, don't we? Because watt seconds, well, power is equal to energy divided by time, isn't it? And so that's watts is equal to joules divided by time. So therefore, multiplying these, a watt second is a joule. Okay, so if we take that 0.035 and we times that by 1,000, that gives us the energy in watt hours. Let's go with that first, why not? But then if we multiply by 3,600, that gives us it in watt seconds. So that gives us 1.26 times 10 to the 5 watt seconds, or in other words, joules. Cool, there we go. Let's use this now. So we're talking about energy used is equal to power times time. And so that is 340 times by 39. So that is 8.7. I don't think we need to go to that amount, do we? So that gives us 13,260 used. This is stored. So therefore, the percentage used, we want a number between 0 and 100%. So therefore, we're going to do this amount used divided by what we had stored. I'm just going to write that out in full, methinks. Why not cancel one of those? And then we're going to times that by 100 to turn it into a percentage. And that gives us 10.5%. 5.4, we have a maximum flight time of a few minutes. The battery accounts for about 15% of the helicopter's mass. Okay. Students suggest that adding another identical battery that doubles the energy available to the helicopter would double its flight time. Deduce without calculation whether the student's suggestion is correct. Okay, so 2 batteries equals double the energy stored, okay, but increases mass by less than double. Therefore, yes, would fly for longer. Why is this a 3-mark question? Oh, okay. It wouldn't double its flight time though. Yeah. It would fly for longer. However, we say that greater force from blades needed to hover. Therefore, blades need to spin faster. Therefore, this would only be true. I mean, what a stupid question. It's obvious, isn't it? Why do we need to go through this rigmarole? This would only be true. This would only be correct if extra battery didn't increase mass. Oh my days. Do you know what? Screw this question. I'm done. I hate these kind of questions. Oh, we're still going with this chopper. Blowing neck. It's moving upwards. At this point, the helicopter stops rotating. We've been given a height. Okay, so it is actually going upwards when it thingy. So it looks like this is going to be a SUVAT question, I guarantee. And so we have our S is our height. We have the gravitational field strength, also known as acceleration due to gravity, is minus 3.72. So the only time that we're really concerned with putting minus in the SUVAT variables is when we have things going in different directions. So if we have something moving opposite to the way that it's accelerating, otherwise we can just keep everything positive. But in this case, we do have to do this. So U is 0.55 meters per second. What else have we been given? Calculate the time taken for the helicopter to reach its maximum height. Okay, that's fine. So they've been nice, actually, for once. They're actually forcing us to split the question into 2. So it's doing this, and then it's coming back down. So we're just being asked to find the time here. So that's fine. So therefore, we know that at the top, at the apex, the speed is going to be 0. We're looking for this. So we're going to use V equals U plus AT. And so therefore, we can just say U equals AT. That's fine. Again, we don't actually care about the minus because we're not caring about this bit for the time being. If we all did it all in one go, then yes, we would. But that's fine. V disappears, doesn't it? So therefore, T is going to be equal to U divided by A. So that is 0.55 divided by 3.72. And that's just going to be 0.1. Let's do that to 3 sig figs for the time being. Okay, 5.6. We're actually now being asked what's the height to go down to the bottom. So actually, they were being nice, but now they're not being nice. So we're doing SUVAT again. But this time we do need to consider our minuses and that kind of thing. So S is equal to something. We want that to be a minus, ultimately. And so U was 0.55. V is minus 2.2 meters per second because it's coming down. as it hits the ground, of course. And then A, which way is it accelerating? It's accelerating downwards, so it has to be minus 3.72 meters per second squared. And we don't care about time. So we're going to use v squared equals u squared plus 2as. Let's put u squared over the other side. And then just divide the whole thing by 2a. And that will give us our s. So that's going to be 2.2 squared. Yes, it's minus 2.2 squared, but it's going to be positive in the end. Take away 0.55 squared, and then divide that by 2 times minus 3.72. And that gives us minus 0.61 meters. So that's just our distance. That's our height. Our height is just 0.61 meters. We are still going with this question. Good grief. Student suggests the acceleration is constant from the instant the blade stops rotating. Okay, discuss this suggestion with reference to an appropriate Newton's law of motion. What? Yeah, we've been told that there's no drag forces. Therefore, the weight is the resultant force. This is constant. So therefore, acceleration is constant. Therefore, as F equals ma, A is constant. What the heck kind of question is that? Way to end on a high note there, AQA. Okay, let's crack on with some electricity. 6.1, what's meant by EMF? EMF is, this is just a definition you need to know. It's a voltage, isn't it, of course? And voltage is energy divided by charge, and so that's what we need to talk about. But an EMF is a PD rise, as it were. It's energy being supplied to charge, so it's the energy supplied to, we just say unit charge, we don't need to say coulombs, because definitions should avoid actual units. We just say unit charge, etc. Now, their definition talks about chemical energy. I flipping hate this. I mean, it's stupid. It really is stupid. It doesn't matter where the EMF comes from. The point is that it is just energy supplied. We don't need to talk about chemical energy, but AQA think that we do, so there we go. So we say chemical energy converted to electrical energy. Oh, that makes me so mad. Per unit charge passing through a battery. That's what they want you to say. Chemical energy. Why do we care? We don't. All we care about is, it's just joules per coulomb. We don't care about where that energy comes from. Maybe it's the cold that's making me mad. No, it's AQA. So we have this resistor. We have a bunch of LEDs. They're diodes. So current only flows in one direction, of course. I can't be bothered to draw all the arrows, whatever that'll do. And we have the current of, let's say, 0.44 amps, 0.044 amps. Calculate the number of electrons that pass a point in 37 minutes. Right, okay. Whenever it comes to number of somethings in a question, you need, again, units are your friends. That's what you need to be thinking about, all right? Let's talk about this. So we have a current, don't we? We have current of 0.044 amps. Now, what is that? That's the same thing as 0.044 coulombs per second. Okay, but then what do we know the charge of an electron is? So charge of electron, that is equal to 1.6 times 10 to the minus 19. And so we can say that's coulombs, but we can say coulombs per electron. Makes sense? So make up your own units in this case. It's coulombs per electron. So we have coulombs per second, coulombs per electron. What can we calculate with these two things? Well, we can calculate electrons per second. So therefore, we can do, well, which way around does it have to be? We need to keep per second, so that has to be on top, doesn't it? Because we can't have that being flipped. So coulombs per second divided by coulombs per electron, and the coulombs cancel, and the electron ends up on top. So we end up with electrons per second. So what does this end up being? 2.75 times 10 to the 17 electrons per second. And, well, we have electrons per second, but we want electrons that travel in 37 minutes. So all we have to do is times that by seconds in a minute, times that by the number of minutes as well. So we're getting rid of seconds to the minus 1, as it were. So times that by 37, times that by 60, and that gives us 6.1 times 10 to the 20 electrons. You could, of course, just used Q equals IT. You could have figured out the charge first and then done a similar thing. There's two ways of doing it. 6.3, we have this graph for an, well, it's a diode, isn't it? So we know it does this and it does that. So current is there in milliamps and PD on the bottom. When does it start going up? 2.5. Determine the power output of one LED when the torch is on. Okay, so we're talking about 44 milliamps. We can see that. So going across from 44, once again, they expect you to be able to read to 1/10 of a little square, which is just stupid. I think that's something like, it's a little bit over 3.4, but whatever. So that goes to 3.4 volts. Cool. The power output then, so power is equal to IV, and so that's 0.044 times by 3.4, and that gives us 0.15 watts. Easy so far there. 6.4. Battery has an EMF of that internal resistance. Okay, fine. So EMF is 12 volts. Internal resistance, little r, that's 1.5 ohms. Determine the resistance of R. Okay, right. So we are gonna have to figure out what the PD is across the whole thing. Okay, so let's write down our equation. So EMF is equal to IR plus IR. We don't really, do we need that? Or we're going to use V instead. We are going to need that, I think. Yes, we are. Because we have the LEDs involved. So this is for R plus the LEDs. Okay, so what are we going to do first? Well, we are going to find out what the resistance of each LED is. So the resistance of each LED is going to be V over I from Ohm's law. And we said that was 3.4 divided by 0.044, and that gives us 77, let's go 0.3 ohms. Cool, so times that by 3, because there's 3 of the bad boys in there, and so that gives us 200, let's say 232 ohms. Okay, so we have that. Is it worth me copying this? No, it's a terrible diagram. Let's draw it a little bit better. Okay, I probably should have drawn a wee little R in there. And that's R there. Okay, so we have the resistance of these is 232 ohms. And we have the little resistance, the internal resistance. What was it? My memory is terrible. That's 1.5 ohms. Okay, this of course is 12 volts. Cool. So it seems like it's not going to be too hard to figure everything else out now. What do we have? We have this, we have this, we have this, we have this. So basically, let's just find out what this R is here, shall we? So, rearranging this. So, let's do it one step at a time. So, epsilon minus I little r is equal to IR. And so, therefore, taking the I over the other side, we end up with that. And so, we could just rewrite it as this. EMF over the current, take away the internal resistance, which makes sense. So, that's going to be 12 divided by 0.044. minus our internal resistance there, and that gives us 272 ohms. So if the resistance of, this is for everything, isn't it, this here, so therefore this R of the resistor is just going to be this 272 take away 232, so I think it's going to be 40 ohms. They've gone to 38.8, whatever. Why have they gone to 3 sig figs there? That's really, that they shouldn't have gone to 3 sig figs, because the internal resistance is 1.5. Oh, the masking says condone answers from 38.5 to 39.7. That's really dumb. That's very unfair for you to not get the marking. Because our values here are to 3 sig figs, it's very unfair for them to expect that to be 3 sig figs afterwards. 6.5, we have an appliance now. Do I have to copy this thing? Okay, what's going on? We have an appliance. Oh, we have a switch too. Okay, each LED requires a voltage of at least 2. So V min for the LEDs is 2.9 volts. Deduce whether the LEDs will light when S is closed. The current in the battery is 3.5 amps when switch S is closed. Okay. The first thing we can do is crack out the thingy again, the internal resistance equation. This, of course, is the terminal PD. And so basically, we can find out what this is. So V is equal to just epsilon take away IR. So that's going to be 12 take away the 3.5 amps times the 1.5 ohms internal resistance. And that gives us 6.75 volts. So there's 6.75 volts available to the circuit. And so that means that the PD across here will also be 6.75. Okay, that's not looking good, is it? Because 6.75 divided by 3, well, it's going to be less than 2.9, isn't it, basically? So that's 2.25. So it doesn't matter what's going on with the resistor there. It doesn't matter how much it's taking, even if it's taking 0 volts from that 6.75. Therefore, not enough for each LED. So I hope you found that helpful. If you did, please leave a like. And if you want to see the paper too, then click on the card and it'll take you to that. All the best. See you next time.